Hello and welcome. My name is Ravi Ozarkar, and today I'm going to talk about response spectrum analysis. This is part 1 of 3, and in this video I'm going to talk about the background of response spectrum analysis procedure. Now, response spectrum analysis procedure is used to analyze your structures for seismic events. So basically, for doing this type of analysis, first you need to provide computer programs with a response spectrum curve. I want to give you some background about how these curves are produced. First of all, you may have to use codes such as ASCE 7 to come up with these response spectrum curves. What these response spectrum curves are supposed to be are basically it's an experiment. So let's imagine that we have a shake table, which is supposed to represent ground. And by shaking this, we're basically trying to mimic a seismic event. And on top of this shake table, we have columns, which are supposed to represent buildings, bridges, towers, pipe racks, you name it. And these columns have different periods or different frequencies. So when you shake this table, you're going to get different behavior depending upon the period and the frequencies of the structures. So to represent these structures, we're going to represent them with mass and stiffness. So the way we idealize these structures are basically using springs in computer programs. And by springs, we mean that they have a K value or a stiffness. And then they also have mass, which is represented by these blocks at the top of these structures. Now, when you shake this table, you get deflections in all sorts of directions. Now, your task is to go in and record the observations from this experiment. And what we do is record these observations in Excel or in a table. In this case, we have recorded the period and the acceleration of each of these structures due to this seismic movement that we're trying to mimic. We take this data and plot it in Excel, and we obtain this curve. This is called the response spectrum curve for that event. From this curve, I can basically tell, okay, if I had a structure with, let's say, 0.5 seconds period, I can calculate what the acceleration is supposed to be. So I take this data, which is basically a single degree of freedom data, and try to apply it to a structure with multiple degrees of freedom or more complex structures. Now, the question that you may have is, how do we calculate the period of the structure? And how do we calculate the mass of the structure? And how do we calculate the stiffness of the structure also? Okay, so how do we calculate all these things is a big question. So let's begin with a very small, simple example. So the way you calculate period is using this formula, which is T is equals to 2 pi multiplied by root of m over k. M represents the mass, k represents the stiffness. M, which is the mass, is basically the weight of the structure divided by the acceleration due to gravity. Now let's try to apply that knowledge to more practical structures. So here I've taken a picture of a wind turbine, and you can see this wind turbine is not a small structure. You can see the fence line, and that fence line looks tiny at the bottom of the screen. You can basically gauge how big the structure is. But that doesn't matter. We can idealize even big structures using this simple concept of stiffness and mass. So the column can be idealized as K, which has a stiffness, and the turbines at the top, or the machinery that's there at the top, which is pretty heavy, can be idealized as a mass component M. So we just have a spring and a mass component, and at the base we have a rigid foundation, and that foundation sits on soil, and we expect the ground to move. By the way, this wind turbine is in a seismic zone, so this needs to be designed for seismic ground motions. So we could do a response spectrum analysis and calculate the expected forces coming on the structure and design the structure accordingly. Let's try to expand this knowledge to even bridge structures. Now, bridge structures are designed using AASHTO code, AASHTO LRFD code. And if you go to even like AI AASHTO specifications 8th edition 2017 code, they talk about response spectrum analysis also. So a bridge structure is more complex, but you can see that we can idealize that also using this simple M and K concept that we introduced. So for example, imagine that bridge that I just had photographed. That bridge is a concrete bridge which consists of a box girder on which you have your roadway, and the trucks basically pass on top of the roadways. This box girder is supported by a column, and the column is supported by foundation which rests on soil. So if you take a section of that bridge, section A, you can see at the bottom of the screen I have drawn the section. I show basically the foundation, which supports the column, which supports the box girder, and the box girder supports the roadway and the barriers. But you can idealize this also using the same concept of K and M, which is basically a column with a mass attached at the top. Okay, so that's how we prepare the structural analysis model. Now, how do we calculate the stiffness of the structure? We basically use this formula, K is equals to 3EI over L cubed. Now, you don't have to do this because computer programs do this for you, but I'm just showing you some simple examples, hand calculations that you can use to understand what computer programs do in the background, okay? So, given the deck self-weight, which is 22.5 kip per foot, and the column length of 25, and the EI, or the stiffness of the structure, is basically 600 times 10 to the power 6, we could calculate the K value, and the K value in this case is 66.7. Step number 2 is we calculate the mass of the structure. Mass is basically weight divided by the acceleration due to gravity, and that turns out to be 12.6. We use those two quantities to plug into this time period equation that I had shown earlier, and we calculate the time period to be 2.73 seconds. Okay? So enough of background. Now let's see how we can use this knowledge to model real life structures inside computer programs. After you calculate the time period, you can use the response spectrum curve to come up with the acceleration. Mass times acceleration gives you force, seismic force, and you can use those seismic force to come up with force distributions and so on. Okay, so let's look at the next video, which talks about how to model structures inside GT STRUDL and use the response spectrum analysis to analyze those structures.